Hello, can you hear me?
Good afternoon, sir. Loud and clear.
Yeah. Okay.
So everybody is taking the tea, sir. Within few minutes, they will start.
Okay. Okay.
Will ask him.
Mouse में रखा है.
Oh, acha. Hi. Deepura, can you hear us?
Yes, loud and clear.
Okay, fine. Yeah. So we'll start shortly.
Okay. But the auditorium is not available. You're having it council room.
Yes, there's another conference with these.
Right.
Japanese-
Japanese team is there, no?
yeah, Japanese game. So yeah,
Yeah.
but still, I mean, we are still waiting for audience here. Still.
We also have a paper where we study Alfvén waves with Dykist. So we have the Dykist transverse waves, as you also seen in the published paper. But then on top of these transverse waves, there's also rotational motion.
Tom van Durselaar in Dutch means Tom from Durselaar.
Yeah.
Tom from Durselaar. So we have similar names in India as well. So Tom has done his PhD from KU Leuven in 2006. And after that, he moved to University of Warwick in UK. He has worked as a postdoc there with his personal grant of Marie Curie Fellowship for 4 years. After that, he moved back to KU Leuven, where he joined as a lecturer, or after a year, you became a lecturer 2011. And then he became full professor a few years ago. How long?
Half a year ago.
Half a year ago, okay. So in KU Leuven, there is this part professor and full professor after you become a lecturer. So he became full professor just half a year ago. So we have both Vaibhav and I are fortunate to work with Tom as a postdocs previously, and we have continued collaboration since at least 10 years or more than 10 years. So we are. It is our pleasure to host him here, and we will. Tom works mostly on all aspects of magnetohydrodynamic waves in the solar atmosphere, whether it is observations, whether it is simulations, whether it is modeling theory, analytical theory. So he works on all essential aspects of magnetohydrodynamic waves. So we will hear more from Tom. Please go ahead. Thanks.
Thank you for the introduction, Krishna. But I should say that I was also lucky to have you both in so it's the luck is on both sides. So indeed, I do a lot of models, and today I want to tell you about my models for global solar corona models driven with both Alfvén waves and kink waves. And I will explain what I mean with that. Especially because there are some people here who are not very much at home in solar physics. Yes. So let me start from the coronal heating problem, just for the people who don't have the background. So on the left, you see the AIA image in the visible light, and there the sun seems almost homogeneous, except in a few small places which are called sunspots. I think everybody is familiar with that. And these sunspots are magnetic places of strong magnetic field. And these places of sunspots, they will translate to active regions, which are seen in plasma, which is emitting at 1.5 million Kelvin temperature, within connected coronal loops, which are following more or less the magnetic field. In the polar regions, you have the open field, which are stretching into interplanetary space, and there you have the coronal plumes. So these are terminologies I will use later on in the talk as well. So just to make sure that everybody knows about these terminologies. And so the question is, why is this so much hotter than the solar surface, which is obviously on a different plate scale here? So yes, just to make the problem worse for coronal heating, on the left-hand side we have a graph of the temperature in the dashed lines of the photosphere. So the temperature goes from around 10,000 Kelvin in the chromosphere up to 1 million Kelvin in the solar corona. And on the right-hand side, you have a graph of the radiative losses from the solar corona as a function of temperature. So for 1 million Kelvin, you have very strong radiative losses. So you can make some estimates, some back of the envelope estimates for energy losses from the corona. So for a temperature of 10 to the 6 Kelvin, a density of 10 to the 15 per cubic meter, which is the typical value, you would get an energy loss of 10 to the minus 15 watts per square meter, per cubic meter. For an internal energy corresponding to 10 to the 6 Kelvin of 2 times 10 to the minus 2 joule per cubic meter. So if you take the ratio of those two, you would get a time scale of around 2000 seconds, which is around half an hour to lose all the internal energy of the plasma in the corona. So indeed, there is a coronal heating problem. Within this 33 minutes, you must resupply the energy at every point in the solar coronal volume. And so that is called the coronal heating problem. So here I wanted to make the point about the magnetic connection of the coronal loops, which is a bit choppy. But so these are the background is the blue and red is outgoing and ingoing magnetic fields at the solar photosphere, and then the white color is the solar corona at 1 million Kelvin, and you clearly see these loops, which I said are magnetic connections between the positive polarity and the negative polarity, connecting both from one side to the other. So as I said, typical values for coronal loops is a temperature around 1 megakelvin, a length of maybe 100 megameters, so give or take a factor of 10 maybe, and then a density of 10 to the 9 per cubic centimeter. So the source for coronal heating is pretty obvious. The source for the coronal heating is the motions of the photosphere. This is a movie by the Swedish Solar Telescope, which has a very high resolution and is zooming in into the visible light that is there from the photosphere. And you see these convective motions, which are just convective cells as you're used to when you're cooking rice, I suppose, in your case. And then these all have magnetic fields, so these bright regions have a strong magnetic field, and these are constantly being pushed back and forth. And that is generating the pointing flux into the solar corona. So this is the source of the coronal heating problem. So the big question for coronal heating is, how is this energy flux from the photosphere, how is that transported into the corona? And how is that energy being dissipated in the corona to keep this heat on a time scale of minutes, as I explained. Yes. So because of that, there are two families of heating mechanisms. So on the left-hand side, you see the DC heating mechanism. And in that case, the photospheric timescales, so they have a typical convective turnover timescale. This is compared to the timescales of these coronal loops, which have an Alfvén crossing time. And so if the timescale of the driving is much longer than this Alfvén crossing time, your magnetic field will get gradually more and more complicated with current sheets. And eventually it leads to a small scale or large scale reconnection. Large scale reconnection is flares. The small scale reconnection leads to so-called nanoflares, which also may heat the solar corona. I will not talk about this, but I will talk about the AC heating mechanisms, where the AC stands for wave heating mechanisms, where the turnover timescale is very short compared to the Alfvén transit times in the coronal heating, in the coronal loops. And so instead of tangling the field, it will launch magnetic waves into the solar coronal loops. And so that's what I'll be concentrating on in this talk, these AC heating mechanisms. So also to give you a background on plasma physics, I think most of you know about this, but just stop me if you want more explanations. So plasma is a gas that is ionized, and it occurs very many times, well, many places in the solar, in the universe, and I'm concentrating on the solar corona, but also, for instance, flames are also plasma. So that's the most familiar plasma, I think. And we describe the MHD, the plasma with the MHD equation. So I'm purely working in the MHD regime for the plasma, which takes the fluid equations. So this is conservation of mass, conservation of momentum, and then energy equation, complements them with the induction equation, and includes the Lorentz force. So that's the basis for my theoretical framework. And of course, there's always the absence of magnetic monopoles, which is there as the initial condition. So then in a plasma, this Lorentz force may be decomposed into two forces, which is the magnetic pressure force. And this magnetic pressure force is pointing transversely to the magnetic field from regions of high magnetic field to low magnetic field. So it's if you have a concentration of magnetic field, it will be pushed outward. The second term is called the magnetic tension. When the magnetic field is bent, then the magnetic field will tend to straighten out. Yes. So the key point here is that there's this Lorentz force. It's called Lorentz force, but in fact, it's two forces: magnetic pressure and magnetic tension. And so the combination of these forces leads to, in fact, three forces in the which are important in the solar corona, which is this magnetic tension, which I just explained, the magnetic pressure gradient, but then of course the gas pressure gradient is also there, like we have in the air. And so we have three forces, and this leads to the occurrence of three waves associated with these forces. So the magnetic tension has its own wave, it's called the Alfvén wave, and this is oscillating with the Alfvén frequency, which has the Alfvén speed, which is determined by magnetic field and density, and then Kz is the wave number along the magnetic field. On the other hand, the magnetic pressure and the gas pressure, they either interact constructively or destructively. If they constructively, you will have the fast waves. They propagate isotropically, which has this frequency, which is denoted with this one, omega f. And then the slow waves, when the gas pressure and the magnetic pressure act out of phase, then you will have a minus sign, and then you have the slow waves. So just to show their behavior in a uniform plasma, this is a simple simulation. It's just a 2D simulation with a magnetic field pointing in this direction. And then there's a perturbation in the center of the domain. And then you can see how this plasma will evolve over time. This wave is being propagated out. So this spherical wave here, this is the fast wave. This is propagating isotropically in the solar corona. The blue wave is the Alfvén wave, which is propagating only along the magnetic field. And then there's the two blobs in the middle. This is the slow wave. This is also more or less along the magnetic field. There's very little deviation, and they propagate at a much slower speed than the fast wave and the Alfvén wave. So this is the propagating with the sound speed. Okay, so I will also show you some equations. Like Krishna said, I like analytical theory, and I think it's very helpful to think about analytical theory because it gives you some insight. And so I start with this textbook Alfvén waves to explain where I'm going to. Yes, so this textbook Alfvén waves, which I showed on the previous two slides. We start in a uniform magnetic field. In the previous slide, it was in the x direction, but here I take in the z direction, and in the rest of the talk, I take in the z direction. I take a uniform density pressure, no flow, and I take a wave number in the x, z direction, so along the magnetic field and one component across the magnetic field. And then you get the, as many of you, or maybe all of you have derived, you get this dispersion relation with omega with the Alfvén speed, and proportional to the Alfvén speed. And we know that in this configuration, the magnetic field will be bent out of the plane, so the magnetic tension can act as a restoring force. So magnetic field perturbation is non-zero in the y direction, and the velocity for the wave is also non-zero in the y direction. The velocity in x or z are zero. Magnetic field perturbations in x or z are also zero. But then we can come back to the induction equation, which I introduced before. This is just how the magnetic field is evolving as a result of plasma flows. So you can calculate for the Alfvén wave that this velocity perturbation in the y direction, the magnetic field perturbation in the y direction, they must be related. That's through this equation. You can find a single equation here, which is relating the magnetic field in the y direction to the velocity in the y direction. And then you introduce this Alfvén frequency expression in that expression here, and you get to this relation. So the magnetic field perturbation must be proportional to the velocity perturbation, and the proportionality factor is square root mu rho, which is very similar to this expression for the Alfvén wave. And so this correspondence between the velocity perturbation and the magnetic field perturbation is a motivation to introduce Elsasser variables. And these are very often used in solar wind physics and magnetic MAG turbulence physics. So Elsasser variables are called Z usually with plus minus, and then there's a V plus minus B divided by square root mu rho. And the square root mu rho, this comes once again from this Alfvén wave expression, Alfvén speed expression. So you should see that there's this plus minus sign, and this plus minus sign corresponds then to an upward propagating Alfvén wave and a downward propagating Alfvén wave. And because of this special relation, you see that for an upward propagating Alfvén wave, this Z plus will be 0 and Z minus will be non-zero. But for a downward propagating alpha wave, you get a plus sign, and then it's exactly the opposite. Z plus will be non-zero and Z minus will be 0. So if you have an alpha wave going in one direction, you will only have one Elsasser variable. And that's crucial. Yes, it will only have one Elsasser variable. So this is shown in this simple graph. If the magnetic field is pointing it's in this direction, and then it's sort of lifted by the alpha wave passing by, or the magnetic field is pointing in the other direction, you see that the magnetic field perturbation is in fact pointing the other way. Right? So if it's going up the magnetic field or down the magnetic field, then the magnetic field perturbation is in the other direction, but of course the velocity is still in the same direction. So you see that indeed the Elsasser variable plus will be 0 here, and the Elsasser variable minus will be 0 here because of this exact balance between the two of them. Just showing a physical interpretation of the equations I showed on the previous slide. Yeah. Tell me if you need to ask any questions, or I'm happy to take questions during the talk already. Okay. So these Elsasser variables, as I said, they're very often used in solar wind, and the reason is that solar wind is in fact highly alphenic, is what they call it, meaning that they're more or less described only by these Elsasser variables. And this is shown by these graphs here, where there's Vt is the tangential velocity, and Vn is a normal velocity, and then you have the same magnetic field components on the right-hand side on the same graph. You see that they're very highly correlated, showing that in this section of the solar wind measured by the Parker Solar Probe, these two quantities were indeed highly correlated, so that in fact, most of the perturbations you see there are just alpha waves passing by, or the spacecraft flying through the alpha waves.
So I have a question. So usually you see these type of very strong correlation for both fast and slow solar wind, or only during the fast solar wind?
So what was thought previously before Parker Solar Probe, it was that this fast solar wind was highly alphenic, but slow solar wind wasn't. But now there's the people in Rome are working also on Parker Solar Probe data, and they find that also the slow solar wind can have episodes of very highly alphenicity, even if it's sort of compressible.
Yeah. Because here also your speeds are around 450 km/s, but then you see very liquid. So they are slow alphenic.
Yes. Yeah. Okay, so how are these Elsasser variables used to model the solar coronal heating? Yes, so that's what the topic was, what I wanted to talk about. So if you do the MHD equations, you can combine them in a way, and this was done by Elsasser, and that's why there is a name Elsasser in 1950. So he combined these two equations, the momentum equation and the induction equation, and he found this simple equation in terms of Elsasser variables, with then the alpha speed vectorially along the magnetic field here. So let's first look at the term on the right-hand side to be 0, because that's a nonlinear term, right? So in that case, you see that this is just a simple advection equation with the alpha speed. So the Elsasser variables are propagating along or against the magnetic field with the alpha speed. Yeah? So this is nothing new, and it just shows that Elsasser variables are in fact showing alpha waves. So then the right-hand side is the nonlinear term, as I said, and this shows that if you have counter-propagating waves, then they will cascade and they will form turbulence. So there's this term is a Z minus and Z plus, or Z plus and Z minus. So you always need Z plus and Z minus to get both before you get the interaction. Yes, so you need a wave coming from here, a wave coming from here. They will interact, they will form turbulence, and then we will propagate afterwards, not interacting with any other things. That's how can you see this mathematically? For instance, you take Z plus minus as just a harmonic wave, and then the right-hand side term will have a e to the 2i omega t. Yeah, so it's double the frequency. But then if you take this cascaded or generated nonlinear term, and you would feed it again through this term, you would get to e to the 4i omega t. And so you get to higher and higher wave numbers. And so this is called the cascade in the solar wind, and this is used to produce heating in the end. But as you said, the essential ingredient is that you have two counter-propagating waves. So this is shown in this graph over here. There's a Z minus, which is propagating up, a Z plus, which is propagating down, and then this nonlinear term will be non-zero. So there's two wave packets, they collide, and then you get both of them deformed, right? So that's what the physics is. So how does that lead to heating? So you get this cascade, you get an injection of scale of wave variables from the photosphere, and this is injecting with a certain scale. So this is called the injection scale. And then there's this cascade from 1 omega to 2 omega, 4 omega, and so on to very high frequencies and very high wave numbers. And then at high wave numbers, of course, the Reynolds number will be small, and then of course the turbulent eddies will be so small that they will indeed start to dissipate and heat. And so this cascade is nearly ideal, as they call it, and then here you get the heating. So what is good for numerical modeling is that in this cascade, this slope here and the physics of that cascade is not influenced by what happens at the dissipation range. So of course we know in the solar corona or in solar wind, Reynolds number is, what is it, 10 to the 12 or so. So you have a very long, very high dissipation range, which you cannot model in a numerical model. But in a numerical model, you have an effective lower Reynolds number. So you have a tail off here to numerical dissipation, but in the end, it doesn't influence what is being modeled. Yeah, so that's good for numerical modeling. Okay, so then there's some more ingredients I need to explain how this is used to model the solar coronal heating right now. So this is the paper by Bart van der Holst who introduced the Alfvén wave solar model, which he called AWESOME. Yes, this is an awesome model. So they start from the MHD equations, but then they take this Elsasser variable equation and they form it to modify it to an equation for Alfvén wave energy. This W is, in my notation, WA, is the energy density of the Alfvén wave, plus or minus the Alfvén wave going up, the Alfvén wave going down. Yes, so there's two equations here, and then there's the 8 equations of the MHD. So in the end, there's 10 equations to model the solar atmosphere instead of the 8 for the MHD equations. And what is then done is that this, I've put the energy equation here for just for simplification. In this energy equation, you also take the wave energies as extra energy in the system. And these wave energies, they also get dissipated and being infected. Yeah? So you keep track of the wave energy and how they heat the corona. So how do they heat the corona? You want to model how this cascade is occurring, what I said, with this power law. And this is done through this gamma W term. This gamma W term is modeling the cascade. And in fact, this gamma plus is proportional to gamma minus. It's proportional to W minus because you need the counter-propagating waves. Yes, so that is coupling the plus and minus wave equation. And then if it's damped, then this will lead to smaller W. So then the energy must go to the internal energy, and so you get the heating of the plasma. There's also a reflection term, but I will not talk about this in this presentation. Okay, so this is coming from the 2014 paper, and this was our first attempt at a solar model. And in fact, you see that these are excellent solar models. You have the fast wind region and the slow wind region near the equator, and they have some streamers. So indeed, this is a very good model for using these wave-heated models for the solar atmosphere. The problem is that in these open field regions, they didn't get this model quite right to compare to the observations, and they needed to add extra heating and extra solar wind driving in these open field regions. So this is done, for instance, in the PSI model, which we discussed this morning. They put an extra heating term close by the solar surface, which is sort of cheating. Yes, of course. This is the best they can do, so that's what they do. Okay. So how can I help in this problem? Yes?
Tom, can I ask a question?
Yes.
Yeah, this is Dipankar here. Yeah. So you sort of, presented the wave turbulence part of it. So for the solar wind observations also, the kinetic plasma behavior and all that is also seen. So how do you think that the velocity fluctuations or the density fluctuations, what people observe in the solar wind, how does that can sort of reconcile with your this wave turbulence scenario?
Yes, in this wave turbulence scenario, everything is incompressible. So there are no density variations. As you see.
So that is what precisely I'm saying. But people do observe density fluctuations in the solar wind. So,
yeah,
so that indicate also turbulence, but of more of a kinetic probably description. So how do you sort of that since that is observed, so what percentage of that turbulence versus your wave turbulence you need for a comprehensive understanding of the solar wind model?
Yes, that's a good question. I don't know the answer to myself. Yes, so I think the compressive turbulence is of a lower level than the alphinic turbulence. And I'm aware of this model from Tokyo University, from Munihiko Shoda, who takes this Alpine wave interaction with slow waves or with the density structures, like you say, and this then leads to extra reflections in the Alpine waves, leading to extra heating. So indeed, it's important, but this is not taken into account into any models, as far as I'm aware, except for the people in Japan.
Yeah.
Also,
Also, the fact is, the Kolmogorov spectrum is also seen in scaling in terms of our solar wind. Also the Parker's results do indicate that. So I was wondering what is the percentage of contribution one can sort of attribute to that versus the Alvin models. But because Awesome is not including any of the other component, I guess, is it?
No, it's only including the Alpine waves. Yes, it's not including slow waves. It's not including kink waves, and that's what I will be discussing.
Okay. Okay.
I will maybe come back to your question at the end of the talk, because I have some ideas about this. But first, I need to explain what I wanted to explain before I can discuss about that.
Oh, sure. Yeah.
Okay, so what new ingredients do we have for that we can help this Awesome model, which is clearly doing well, but it needs to do even better. And so we know that there's transverse kink waves in the solar corona. This is, for instance, after a flare, where you see this corona loops oscillating transversely to their axis, and this is called a kink wave, which are different from than Alfvén waves. And so this was only up to 10 years ago, we only saw them after a flare, but now we know that there's also there before and after a flare. So in fact, also during quiescent times. So this is taking a slit across this coronal loop, and then you see that even before the flare, which is occurring now, then you see the classical oscillations. After that, you have these transverse oscillations which keep persisting the whole time. So these are called decay-less kink oscillations. And so they are shown to be everywhere in the solar corona. Including also in the open field region, which is the problematic region for the Awesome model. So what they have done in this Thurgood paper is to take slits across the polar plumes, which are shown here with this white and black intensity structures. And then you see in I think it's slit 2, you see these transverse waves, which is very much like what some of you were showing yesterday. Yes. And so these transverse waves are also kink waves of these polar plumes. Of course, the nature will be very different. The kink waves in loops are standing kink waves. The kink waves in plumes are propagating kink waves. I will focus on these kink waves in these magnetically open coronal plumes in this talk. So kink waves, we can also have a model for that. So they don't propagate with the Alfvén speed, but they propagate with the Alfvén speed. With the kink speed, which is an average of the Alfvén speed inside the loop, which has a higher density, and outside the loop, which has a lower density. So there's also a difference in Alfvén speed. And the kink speed is in fact the average of the two Alfvén speeds. If you calculate the model, the analytical model in cylindrical geometry, so this is just a slice through a cylindrical loop, then you see that the loop is oscillating back and forth, corresponding quite well with this movies I showed you before. So these are mostly incompressible, but still there's an effect of the different density contrast between the interior and exterior. And so another new information we have is that these kink waves, in fact, have a high energy content. So with the solar orbiter, my postdoc Daye Lim, she made a statistical study of these kink waves in closed coronal loops, and she found that if you make the graph of the energy flux on the vertical axis as a function of the frequency of the waves, you find that the energy, in fact, is going up for smaller and smaller periods. And so these smaller periods we could not observe before with AIA, for instance, but now we find that, in fact, these contain the largest amount of energy in them. And so if you integrate the area below this energy flux you find an energy of 10 to the 4 watts per square meter, which is sufficient in principle to balance these radiative losses which I mentioned in the solar coronal heating. So indeed, so the kink waves potentially contain sufficient energy, and so the question is, can they in fact heat the solar corona together with these alpha waves, which seem to work quite well for the solar wind. And so we have done a direct numerical model by Meet Jashir, who's now back in Shandong University, and he made a model of this kink waves in a coronal loop, where he was driving from one foot point, and then you see the loop oscillating left and right, again compatible with what you saw in the movies that I showed before. And the difference is with this analytical model is that this loop doesn't stay as one whole, but it seems to deform. And this is called also, you also see the turbulence formation. So in that sense, it's not very different from Alfvén waves because it forms also the turbulence. And you can take the same pathway as the Alfvén wave turbulence. You cascade the energy to small scales, and there you dissipate with resistivity or maybe viscosity or numerical dissipation. But this leads to heating, and this is shown in the graph here. So it shows an isocontour of 1 megakelvin, which is 1.1 megakelvin. And so initially there's nothing to see because everything is 1 megakelvin. But after that, this is starting to get turbulent, and in the turbulent region, you get the heating of the plasma. And so in fact, this loop is heated by kink waves, only by kink waves. Yes. So that was our first time that we could do that. And so it shows that indeed there is a potential to heat the loops. Okay, maybe I'll skip over this one. And then there's another new concept that we can use to enhance these awesome models. So now we know these transverse waves, but we also know that these transverse waves become turbulent for the standing waves. But for propagating waves, they also become turbulent. So this is a simulation of coronal plumes. So they are rooted in the photosphere, and then they're extending very far into the space. And these are driven at a foot point by convective motions, so something that's resembling convective motions. And initially, there are initially placed, randomly placed strands with density enhancement. And then after they get driven, then you start to see that they also become turbulent. And so initially, there's a kind of cylindrical structure, but afterwards, you see that this is becoming turbulent. And this is shown in this cross section. Here, initially, you have these many strands, which then become turbulent over time. Yes, after several wave periods. Yes. So this is clearly very different than Alfvén waves, because in Alfvén waves, you needed 2 counter-propagating waves before they get turbulent. But here you only have waves propagating from the photosphere up, and they get turbulent even if there is no counter-propagating kink wave or Alfvén wave. Yes, so that's why we named it uniturbulence, turbulence from unidirectional kink waves. Yes. So the question is, why does it become turbulent?
Yes, so I have a question. One was? Okay. So I have a question. I mean, if you change the number of this random with density inhomogeneities, does the time taken by turbulence, time taken to develop turbulence will be same or different?
It will be different. It depends on the density contrast. It depends on the period of the wave. Depends on the separation of the strands. Let's say yes. Okay. Yeah. Very clearly, it depends on that. You also had a question?
No, I think I was wanted to ask why is becoming turbulent. Then you are going to explain that.
I'm going to explain that. Yes, that is a very difficult question, I think, which we've worked on the last 5 years, maybe. Yeah. So for that, I go back to the induction equation, which I showed you before, to get to this Althusser variable. And so we found this equation here, which is saying that the magnetic field perturbation is proportional to the velocity perturbation. And then you can combine these two, this equation into Althusser variables, and you find this single equation for Althusser variables plus and minus on the left and right hand side. And this explains why these kink waves become turbulent. You don't see that. I will explain to you. Yes. So let's come back to Alfvén waves. So an Alfvén wave is propagating with a Alfvén frequency. So in that case, omega equals omega A. Yeah, so this factor will be 0. So this number can be anything it wants, which is an upward propagating Alfvén wave. But then this number will be automatically 0. Yeah, so this is a single Alfvén wave propagating. Yes. And vice versa, if you're propagating down, then this will be 0. This will be any number you want, but this will be 0 as well. Yeah, so then you have the counter propagating wave. So we're recovering what I just explained before. But for a kink wave, I told you, it's not propagating with the alpha speed, but it's propagating with the kink speed. And so neither this term or this factor, nor this factor will be 0, depending on whatever direction you propagate. So both this one and this one will be non-zero at all time for any wave, except for alpha waves. Yes, so any wave will have this property. And so if this is shown specifically in this graph, for instance, if you take this wave vector with a magnetic field in the x direction, the last time, I'm not sorry about that. So then the fast wave will have a blue minus component and a red plus component. And so the fast wave is also composed of a plus and minus component, but also the kink wave is composed of that. And so because of the kink wave has both Z plus and Z minus, it will also experience this cascade term and will also form turbulence. And that's answering your question. That's why the turbulence will be there. So in this case, the
And also, okay, sorry, again, another question.
Yes.
So the equation that you showed, omega minus omega A, Z minus will be equal to omega. Yeah,
Like-
this one.
yeah, this one. So now, of course, when the speeds are not equal to Elfman speed, or when the wave is not an Elfman wave, then both will survive, Z plus and Z minus.
Yeah.
But the question is, whether their magnitudes will be equal, or will it be
They
a
will be-
balance,
no,
or
no.
it will be imbalanced?
It will be imbalanced, yes. There's always an imbalance. So you see in the graph, an upper propagating wave is on the right-hand side. So this is the minus is always larger than the plus for the fast wave, and also for the slow wave. This is the orange and the brown contour. Minus is always larger than plus. On the other side, it's always the reverse. So one is always dominant over the other. Okay, and the ratio of the two of them will be determined by the wave parameters. And so, yeah, why is now the turbulence developing? So this term is always non-zero because the kink wave is upper propagating, but this kink wave always has Z minus and always has Z plus. So this nonlinear term is always non-zero. And that's why you get the development of the turbulence, even if there's only one wave. Okay, so how can we put that in the Oslo model? Right? That was a question. So for that, I need to introduce a new concept. So I explained to you about these Elsasser variables. Elsasser variables are a peculiar combination of the velocity perturbation and the magnetic field perturbation, with a proportionality factor which is 1 over square root euro, as I stressed. So I introduced these Q variables, which are a variation on Elsasser variables with V and B, and you make a linear combination of them, but then with alpha as a proportionality factor. So if you take alpha to be 1 over square root mu rho, you go back to the Elsasser variables. And then I will show you later that this alpha B is in fact the phase speed of the wave in a non-moving frame. So then with this, by adjusting this alpha, to choose a particular wave that you want to track, you can follow any wave that you like. For instance, a slow wave, fast wave, or a kink wave. And I will use the alpha necessary for a kink wave. And so these Q variables are in fact a generalization of method of characteristics, which you may be familiar with, or Riemann invariants, which you also may have heard of, and a Freeman-Rotenberg formalism for spectra in rotating plasmas can also be derived from it. So it's indeed, it seems to be quite general. So then I computed what happens with MHD, and I had this simple equation for Elsasser variables. For Q variables, it doesn't get so simple, but this is the full equation for Q variables, which is very long. And I'm sure you don't understand, because I also don't understand, so don't worry. But this equation, in fact, you see there's a propagation term here for the Q variable, and then there's also a density variation term here. And then there's some source terms on the right-hand side. And in fact, this equation is full MHD. So with this, you can model any phenomena that you like. And it contains everything you know, and it contains everything you don't know. So with this, you can fill your entire career. So, but let's go to more simple cases, because then at least you can learn something from it. So first we go to the Alfvén waves, because that's something we understand, right? So in the Alfvén waves, I can linearize this very big Q equation to only the Y component. And then you find that this, if you want to be co-propagating with an upper propagating Alfvén wave, you need to have this factor to be 0. And it means co-propagating, which means that this delta alpha needs to be 0. I didn't explain that. Delta alpha is the deviation of alpha from 1 over square root mu rho, which is a value for the Alfvén wave. Yes, so that's an important parameter. And so you find that this delta alpha needs to be 0, meaning that you're just recovering alpha in waves. Yes, and then you put this here, and then you find that indeed you find the propagation speed for the alpha. So that's just recovering what I said at the beginning of the talk. But then you can do the same for slow and fast waves. And I showed you the graph before that the slow or fast wave both have z plus and z minus. So for q variables, you can choose the alpha. So that is a slow speed, then only the q minus slow survives, or the q minus fast survives for the fast waves. And you're co-propagating or counter-propagating, only the plus survives. And so with this choice of alpha, you can in fact split the waves in propagation direction. So I'm going to the induction equation for the final time in this talk. So with the induction equation, now I put a background velocity. You can do the Fourier analysis in the z direction, and then you get to this simplified equation. Yeah. So once again, instead of taking the Alsacer variables like I did before, you can make the linear combination to form the q variables. And then you find this equation, which is very similar to the red equation I showed before, except that now instead of having the alpha speed here, now you have the Doppler shift of the wave and then the phase speed of the wave. And this shows that by the choice of alpha, you can in fact split waves between upward and downward propagating waves. So with the slow speed, we will get the splitting between the slow q. Yes. Or by the king speed, you can split again, left and right. And so, yeah, what is the meaning of this alpha? I said it's the phase speed of the wave in a non-moving plasma. So if you take this propagation term and you write it out in its terms, here you get this z dot grad z. That's what I showed before. Now it's q dot grad q. It's the same term as we have in the alpha wave turbulence. So if you leave that out, the nonlinear part, then you just get the linear propagation. So in fact, that shows that this alpha is indeed showing the propagation speed of the wave. Yes, so that's showing that this is the phase speed of the wave. So you always choose the alpha to coincide with the phase speed. Okay, I'll also skip this. So just looking at the solutions for the kink waves, you can also redo the same thing with q variables, and then you get to the results which are found here. This is a connection formula at the boundary of the loop. Maybe some of you have calculated this in your coursework, or maybe re-deriving some papers. So this is the velocity being continuous at the boundary of the loop, and this is the pressure being continuous at the boundary of the loop. And so from that you get a dispersion relation. Normally you get this kink frequency or kink speed, as you have done before, and then from that you can also calculate the alpha that you need to track the kink waves, and this is what we'll need later on. So this alpha, you see, it's just very close to this phase speed here. So that's what we'll need later on.
So, Tom, so mathematically speaking, this alpha should be continuous. Why you have
it's not continuous in this case. No, there's alpha left, or this is just an interface. There's alpha left and alpha right, and they're discontinuous quantity.
No, I mean,
and in this case,
I mean, from the definition of alpha you have, it can have any value.
It can have any value.
So that, but in the reality, you have only these 3 speeds compared to slow,
yes,
and the fast.
Yes.
So
speed
how are you restricting in your formalism that alpha is restricted to these 3?
Yes, so you need an extra equation to restrict it, and the extra equation is that you want to be co-propagating with the wave. So that is restricting the values of alpha that you can consider. Okay. So well, this often happens in mathematics. You have a system of equations you can't solve. You add an extra parameter and an extra equation, and suddenly you find the solution, right? Okay. Yeah. So this is very similar to that. Okay, let's go to awesome, which I said is the MHD equations, and you add the 2 equations for the alpha waves, right? So how can we add the kink waves? We need to add 2 extra equations for the kink waves. So it will be MHD, 8 equations, 2 equations for the alpha waves, and 2 equations for the kink waves. So how can we derive these 2 equations for the kink waves? We start from this Q variable equation, and we use the alpha that we just derived in a simplified setup. So from that, I just linearize this very large equation, which I showed you, which is still a complicated equation, but then you take some additional assumptions that is nearly incompressible. So the density variation is 0. So in contrast to what Dipankar was asking, and that there's only perpendicular components of the magnetic field and velocity perturbation. And so then it simplifies. And then you do a scalar multiplication with this quantity to get to energy density. So this also reminds you of the equation for the Alfvén wave, which was written in the Alfvén wave energy density propagating up or down. Yes, so this is the kink wave energy density, which is a sort of average of Q up and down. So then you get to one single equation, which is this one. And this is very familiar to you because it's in fact exactly the same as the Alfvén wave equation, except now there's WK for kink wave instead of WA for Alfvén wave. Yeah, so the left-hand side is exactly the same. It's only the right-hand side which is different. So the right-hand side is the cascaded term for the kink wave, for this unit turbulence, and this is then cascading to small scales, leading to heating. And so this term is leading to heating. And it has this L perp, which is also occurring in Alfvén wave turbulence, but in Alfvén wave turbulence, it's a free parameter. Here we have this L perp to be in terms of the radius, the filling factor, or the density contrast, which you can also take to be a function of the space in the solar corona. So just a direct comparison, in the right-hand side in the Alfvén wave was this gamma, which I showed, and this gamma was proportional to W minus or W plus, yes. So this is the L perp I was mentioning, but now we have this kink wave, which has this dependence, which is nearly the same, except that there's no cross propagation, counter propagation needed. There's W plus, which will cascade just on its own. There's W minus, which will also cascades just on its own. Yeah, so that's the key difference. So it means that the kink waves will also start damping immediately when you drive them from the photosphere in the coronal plumes. They will immediately start heating. Whereas Alfvén waves, first they need to propagate up, you get reflection, and then you get the counter-propagating waves and they will heat. And so it takes more time and more specific conditions to do the heating. So with this, the kink waves, they will also always heat, and they will start heating low down in the atmosphere, which is exactly where the problem was with the Olson model. Yes, so with this kink wave heating, you can in fact fill the required heating in the lower part of the atmosphere. So I'm showing you the equation. So this is conservation of mass for the background, induction equation for the background, momentum equation. But now instead of just having the gas and magnetic pressure, you also have the Alfvén wave pressure and the kink wave pressure, which are pushing the plasma up and are accelerating the solar wind. Then there's the energy equation, which also now not only has the Alfvén wave energies, but also the kink wave energies. And then there's the work being done by the Alfvén waves and the kink waves on the plasma. Okay, so we can now make a numerical model with that, with these 12 equations. So, and for that, I used the Python package PhyPy. So if you want to experiment a bit yourself, you can just use this package to write differential equations. Yeah? So it may be quite interesting for you. So for instance, the continuity equation is written in this way. It's the transient term is this d by dt of density, name for density. And this is minus the convection term of v dot grad density. Yeah, so in fact, it's quite simple to implement. So even if you have just another differential equation, you may just use this package yourself. And you don't need to take care of discretizations and so on. So I show you the graph of the first 50 seconds of my simulations as a function of height, which is going from 0 to 100 megameters, probably you don't see in the back. And this is showing density, the velocity of the plasma, the thermal energy, the temperature of the plasma, and then the downward propagating wave and the upward propagating wave energy density. And so, of course, the downward propagating wave is coming down. Very good. The upward propagating wave is going up. Very good. But you see that this is damping. And this damping is leading to the heating due to the turbulence. And this heating is then compensating the radiative losses in this region. And so this is just a cut at a specific time after 20 seconds. So 1 megakelvin is the initial temperature. And then there's 3 simulations. The red one is only with kink wave heating. So you see that the temperature goes up. So kink waves indeed heat low down in the corona from 0 to 100 megameters. Then there's a green simulation, which is the simulation where there's no kink wave heating, only radiative losses. So of course it's cooling down. And then the orange one is the simulation with both radiative losses and kink wave heating. And you see that the temperature is higher than the radiative losses. So for now, we can't really heat the corona, but at least it's close enough that we can bridge these parameters. And one of my PhD students is working on this to find for which parameters can we get a reasonable heating? And can we get to a equilibrium state?
So what parameters are you changing to get to the?
Putting more energy, putting more higher magnetic field to increase the point flux, for instance, changing density contrast.
So for these calculations, you use these parameters from the observations or?
Yes, I just put some random values, like radius is 1 megameter, density contrast is 3, like all simplified values. Density is 10 to the 9.
So this is only T equal to 20 seconds.
Yes.
Okay. So that means that within 20 seconds it cools down if enough energy.
Yes. The radiative losses are very strong. As I said, 2000 seconds is your cooling time scale. So that's your e-falling time scale. So this is the first part of the exponential. So it's cooling down extremely rapidly. Yeah. Yeah, but then, this is only 20 seconds, but I also ran it to 3000 seconds. And then you see, okay, there's still cooling here, but the temperature at least doesn't rapidly crash. So indeed, it can sustain against its radiative losses, which I said would lose the energy within 2000 seconds. At least here, it doesn't. Yeah, so it can at least maintain the corona in this region. And so in that sense, it's promising. Indeed, my PhD student found regimes where it does work and keeps the corona stable. And you see that also that the velocities here have a magnitude of maybe minus 10 to 10 kilometers per second, which is what is required to drive the solar wind from these regions. And so that's also promising to do that. So what are we doing now is the 3D modeling in AMR-VAC with a new physics module, including this Alfvén and kink wave heating. So there's the 8 equations for the MHD for the background, then 2 equations for the Alfvén waves and 2 equations for the kink waves.
Just a question from previously. So how fast there are 2 things, right? If there is a large wave amplitude and how fast you can dissipate and supply the energy.
Yes.
So you play with those both parameters so that you can compensate for the energy.
Yeah.
So even if you have a smaller wave amplitude, if you are able to dissipate efficiently, then you are able to give the energy.
Yeah, that's right. Okay. So the higher the density contrast, for instance, the more rapid the dissipation.
Okay. So that parameters you play around so that
yes, that's
enough
right.
energy is supplied.
But of course, the higher the density contrast, the more rapid your loop will cool down. And so the low is a fine balance.
Tom, one more thing I just see. Yeah, if we could go back to the previous slide. Yeah, so you actually been able to generate very high velocity fluctuation beyond say 60, 70 sort of meters. And the top part.
Yes.
Right, exactly there.
This is a numerical mistake, a numerical error. So this 5-pi package is useful to experiment with, but it also introduces numerical errors, which are hard to circumvent. So this is also something we're working on, how to remove that from the Python code. Okay, so as I said, now we do the full 3D modeling in AMR-VAC, which is just finished. So this is a first snapshot of the 3D simulation. And in this case, the magnetic field is uniform everywhere. So in fact, it's not very realistic. And so what Max, my postdoc, is doing is showing this wave energy. So the wave energy is red is high energy, blue is no wave energy. And then you see that this is propagating up. Wow. It's a kink wave propagating up in a very complicated setting. But what is more important is to see that the kink waves are in fact heating. So this is temperature and it starts from 1 megakelvin, but then as the waves are propagating up and now dissipating, you see that the temperature higher up is increasing to higher temperatures. And so in this case, indeed, you can heat the solar corona even in this 3D setting. And so this is just a proof of concept that in fact we're getting close to doing 3D simulations of global models with kink wave and Alfvén wave heating.
So you're getting hotter temperatures on the tips, similar to the SPQs, type 2 SPQs?
Yeah, this is so this is a height probably of 100 megameters.
Okay.
Yeah, so it's really well beyond the spicules.
Yes.
In fact, in the chromosphere, this turns out to be quite difficult because when you have the temperature, the transition region, then there's a large reflections of kink waves and Alfvén waves. So that turns out to be quite difficult.
So this dissipation happens until all the wave energy is exhausted.
Yeah, so I'm going back to the previous graph. So the wave energy is propagating up, but you see that also the wave energy is damping. So of course, if the wave energy is damped, of course it cannot heat anymore. Yeah. So you will get heating in the lowest, maybe 100, 200, 300 megameters, but beyond that, the alpha waves should take over. But the King waves can play the role low down in the atmosphere.
So I'm thinking in terms of, I mean, this is for open loops. If you have closed loops, for example, so you have a similar pattern of increase in temperature as you move
Yes.
towards the apex, but that is not a consequence of dumping more and more energy as you move towards it. Even if you have a uniform energy dumping all along the loop, you will end up in having higher temperature at the loop apex because of the energy balance between the
Yes.
radiation, conduction, and
Yeah,
this thing.
conduction is very important.
Yes.
Yes.
So that is not included.
Conduction is included.
Is
here.
included.
Yes, yes.
So
Everything
then
is included.
still here, by propagating the waves, you're gradually dumping more and more energy at the top.
No,
No,
there's gradually less and less energy.
less
But then
and less.
the conduction will heat up the loop top. Well, will redistribute to the loop top.
So this is a balance between all the three, so
Yes.
that you're
Yes.
still then in a closed loop you reach an apex temperature, right?
Mhm.
So what happens in an open loop then?
These are all open loops.
Yes,
We
so-
haven't done closed loop yet.
So then, I mean, then in this case, do you reach a threshold temperature or something?
I don't know.
Okay.
We haven't tried it. I don't know. Yeah, but then you should see the heating also has energy coming in from both points, and then they will also
Yes.
yeah.
Yes.
I don't know. This is something we'll still have to do.
Tom, what is the scale of this? I mean, since you mentioned 3D, what is the spatial scale in X, Y?
So this is just the full solar atmosphere is just represented a bit weirdly because it's only say 100 by 100 pixels or maybe points on the solar surface, and so in that sense it's not very well
Yeah, so
resolved.
what Krishna was saying, there is no difference between closed or open and all that. Everything is open. If it is distributed
Everything is open.
across the whole sun, then that is the scenario he's trying to.
Yes, that's right. Yeah.
Yeah.
So just to see if the 3D module is going to be working.
Yeah.
Okay, I come to the conclusion. So I talked to you about the solar coronal heating problem, and I talked to you that maybe waves could play an important role in this. And so when the plasma is structured in loops and plumes, the kink waves are starting to play an important role, as I showed. And these kink waves, they become turbulent, even if there's no counterpropagating waves, and we call this uniturbulence. And so to track the heating of this uniturbulence, we needed to invent the Q formalism, Q variables, and then we built the two extra equations needed to make the U awesome model instead of awesome, U awesome, to have the kink wave heating model for the solar corona. And so now we're doing the 1D implementation is finished, but now we go to the 3D implementation, and I hope to show next time I'm here that indeed there's a fully working 3D simulations.
Any questions?
Yeah, this 3D, it's not fully spherically coordinate system, or what is it?
It is a spherical coordinate system, yes.
Okay. So in some sense, you could generate the maps, what BART produces in terms of the solar wind.
Yes, that's the goal. That's the immediate goal. Yeah.
Yeah. Okay. Yeah, that would be awesome.
No, you awesome.
You awesome.
Okay, I have a question from the beginning. Initially, you have I think the radiative losses plot, right?
Yes.
At the first, I think maybe first or second, the radiative losses plot. So this corresponds to certain wavelength, perhaps, right? So
No, this is integrated over all wavelengths.
then the visible wavelength should be larger,
But this is for coronal plasma.
only for the coronal
Yes,
plasma.
yes.
Taking considering the coronal plasma, then it is dominant in the extreme ultraviolet.
Yes,
or
yes. You
X-rays.
see that this is stopping at 10 to the 4. So even for the chromosphere, you cannot use these curves. This is strictly for optically thin radiated losses.
Okay. Any more?
So I have
questions?
just,
Okay, go ahead.
So as you said, you are now inclusive of this kink wave heating. You are bridging the gap between the losses and requirement of the coronal heating.
Yeah.
So that part can come only from the small scale reconnection that is occurring,
Yes, that's right. Yes, the reconnection I mentioned it
Yeah,
once and I
in the
didn't
DC
come back
mode.
to this. Yes,
So
so of course this is we didn't take this into our model, but there are other people working on this, and so in that sense it's not a problem because you can just take a DC heating model and, for instance, from Oslo or other places, and our wave heating model, you can compare them, which matches best the observations, and then you can start to discriminate even between AC and DC heating models. The attractiveness of this model is that this turbulent cascade doesn't suffer so much from numerical resolution, whereas the DC heating models, the 3D
Yeah,
heating
they-
models, they're just current dissipation is just ohmic dissipation.
Yeah.
In that sense, they're very sensitive to numerical resistivity. Yeah. So I think it's an attractive pathway to go around
Yeah.
this problem. Of course, it may still be that this is disproven, and in fact, we will find that waves do not heat the corona, but that's also a good result, right?
So, I mean, we have 2 minutes. Anyway, I'll
Yeah.
ask after Upasana if there may-
Yeah, so like in the open flux tube simulation that you showed, so there are different density strands there.
Yes.
So you said that kink waves, they will dissipate because of uniturbulence. So approximately at what height so they will start to dissipate?
Yeah, so as Baba asked before, the damping length is depending on several parameters. For instance, density contrast is an important factor, but also the wavelength or period is also an important factor, the radius of the loop. So it's maybe something between, let's say, maybe 20 to 50 megameters to maybe a couple of 100 megameters. So it's a reasonable scale. I mean, in the sense that it's fitting coronal scales.
Yeah, so it means that beyond that, those heights, we should not expect to see much of a displacement.
Yeah, that's right. Yes. So also when you go to maybe a few solar radii, you also don't see any density contrasts anymore. So of course, then
Yes.
there's no reason that kink waves can exist anymore because there is no structure. And of course, they will not heat anymore. And then the alpha waves will play the major role. It's only in the low part where you have the structure and the plumes and the loops, spicules, there they play the role, in my opinion.
So, I mean, right now, because you have many unknown parameters, sort of like filling
Yes.
factor,
Yeah.
density contrast. So I'm sure, like, I mean, if you tweak the parameters and try to match the model, but then try to match the observations, but then we have currently many mechanisms, right? Like, so ultimately, I mean, how would you plan to distinguish between, so which one works best? Because unless you know these parameters, you can always end up saying, okay, this can potentially lead to whatever is observed, right? So is there any distinguishing factor in your mind, or?
Yeah, so now in these alpha wave heating models, the ALSA models, you have this LPER parameter, which they can put any value that they want. They typically put a value of maybe 1 to 10 megameters, which is just grabbed from thin air, and they adjust it to match the observations. And that's not good because you don't know this LPER, and it's just a fudge parameter, I think always. In my case, we have these parameters, and you also have the LPER, but LPER depends on density contrast, filling factor, radius. And of course, you can still adjust them, but you know limits on these values from observation. So if you have to adjust the radius to be 10 or 20 megameters, you know that there's something wrong. And so in that sense, you can start eliminating physical mechanisms, I think.
Yeah, so this can also be used as a tool for seismology. I mean, if we know
In
certain,
principle, yes.
for
Yeah.
example, if from observations, let's say from right now we have high resolution observation from EUI, if you know what are the strands width approximately, and perhaps then using this we can compute density contrast or maybe some other.
Yes, I think so. Yeah. In fact, I told you there's a deadline yesterday. That was what the project was about.
Oh, okay. So
I have one question. So you showed the turbulence cascade power law. So what will be the like effect of alpha wave on this inertial range loop? Because like in the inertial range, the turbulence cascade is going on where the energy dissipating from large scale to smaller scale. So what will be the influence of alpha wave? Because in MSD there will be alpha wave. Because you showed
Yes.
that,
Yeah. Because of course, now I'm assuming that alpha waves don't interact with kink waves or vice versa. But we have in fact numerical models, direct numerical models, where they do interact and they damp faster when they're both present. Of course, one is creating small scales, and that is more rapidly dissipating the other one. So that's totally right that you say that. And in fact, we also want to model that in the same project that I submitted yesterday.
Okay.
So that's a very valuable question.
Because I mean, in the solar wind also we get this turbulence, but earlier the people like they're only fitting one slope in this inner solar, they are getting -5/3, -3/2. But recently there are studies where they're getting twice two slope in the inertial range,
Yes, yes.
-3/2 at small, like smaller, so larger scale, and -5/3 at smaller scale. So
Yes.
I mean, is due to the like Alfvénic turbulence or what?
Yes, also with the kink wave turbulence, this uni turbulence, you can also get similar slopes. So we did also numerical simulations, and then we got a varying slope between -2 and say -1 or so. So it's also very much in the same range. The issue there is that with a periodic driving, then you're always pumping new energy. Maybe I should go to the graph. This one.
Yes.
So what happens is when you're pumping energy in with the large scale motions, then this is pushed up, and then it becomes steeper, and then it propagates through all the scales because it needs to cascade. But then the wave is sort of in a non-moving position, and it goes down, and then of course this is being put down because there's no energy flowing into the cascade, and so then you have a variable slope here, variable over time. And so this is different than the Alfvén wave turbulence, where they do this steady state turbulence, and they can very precisely measure this -5/3 or -3/2. But in our case, this is not so easy to do because you have the time dependent turbulence. It's also not fully settled turbulence because of this variation of the input energy. Yeah.
Yeah, so I didn't get why there won't be any variation in the input energy in case of Alfvén waves.
They have these boxes, periodic boxes, where they put an equal amount of upward and downward propagating Alfvén waves, and then they can, after some time, they can just make the statistics, and they can very
Okay, so
precisely.
this is for this steady state to reach, or I mean.
Yeah, this is for the steady state, yes.
Okay. And now in your case, you are driving it continuously. So
Yeah.
you have a dependence when you inject more energy, and then.
Yes, yes.
So you have chromosphere in the model? In the 3D, the final.
No, there's no chromosphere then.
So then thermal conduction is not exactly the real thermal conduction.
No. Yeah, so we stop at the base of the corona.
So I have another question. I mean, for example, in case of Alfvén waves, we see a very good correlation in the solar wind data. We see a very good correlation between B and B. I mean, you have also shown that. So in your case, what would be expected? I mean,
It's also highly correlated, yes. So it's the same equation that we discussed already. Yeah, for instance, this, this will also be a strong correlation because this is just a linear combination of them, but they're fixed in a specific ratio. And this is also fixed in a specific ratio, so that they will also be highly correlated.
So there is no way from the institute that we can disentangle this effect from.
I think the difference will be quite small, yes. But we can have a look.
Yeah, I mean, she's already working on some few things we will discuss tomorrow.
Okay, okay.
But she is looking at the variation of these parameters inside CM.
Okay,
Yeah, let's see.
Okay. Okay. Let's thank Tom again. So Tom is available here tomorrow full day. So if any of you want to have a discussion, you're welcome to join him. He's in the visitor room in the first floor of the main building. So anybody wants to join for a discussion, please. You can write to him as well. His email ID is in the email ID circulated for the talk. Okay, thanks. Thank you very much.